So good evening, everyone. It's a real pleasure and an honour to be here this evening and to have this opportunity to talk to you a little bit about some of the research that I and others do in building mathematical models to understand the world as it is around us, but particularly systems and how they work for us. We're going to be talking about mathematical models. There are many different ways in which people try to understand the world by building mathematical models. What I'm going to talk today is one that focuses particularly on resources and the resources that we use, and sometimes when we can't get the resources we want. And so that is what I'm going to talk you through. And a key part of that is something that is very British, which is queues. So queues, as I will explain, are very closely related to resource and particularly limited resource. And we think of it as something very British. We joke about it and think, but in fact it's universal. So this is actually a queue of a Polish post office, and they queue as well. So queues sometimes seem that they're absolutely essential in life. You know, there's no way of avoiding them. But have you ever wondered if we could do away with queues? What would we need to do? Anyone got any suggestions how we could get rid of queues? Think about the post office. Why are we queuing? More counters, exactly. So we could always do away with queues if we had more resources. And we say infinite. We don't actually mean infinite because that's not possible, but in these kinds of models we talk about infinite resource if that means you've always got a resource when you need one. So that would mean when you walked into the post office, another counter would pop up just for you, like magic. And that is often what users would like, actually, but system operators, the post office, not so much. So this is the kind of modelling that I'm going to talk about. We're focusing on that resource point of view to try and understand the dynamics of systems. So resources are key when we look at how systems behave. So, for example, when you go through airport security, another situation where you queue, there are a number of different resources there. You're waiting for your time to get your basket to put in your belongings, and then you need to go through the scanner, and your things need to go through the scanner, and then you pick them up, and you might have to wait for something. The counters we've already mentioned at the post office. These are really obvious resources, but often systems have resources that you perhaps don't think about. So, for example, when we're trying to travel by train, sometimes we can't, the train slows down. I was on a train to Swindon last week. We got stopped because there was a red signal because we couldn't enter the next piece of track. So we can think about train networks of the resources being, the pieces of track being the resources that we need to access. And you can get queues built up when you don't get access as soon as you would like. So, as I say, if it's available immediately, then we just proceed. But when it's not, that's when you get a queue, and then you get additional delays. So if we're trying to tune a system to be as efficient as possible, we don't want to have queues building up, because that means it's going to take us longer to achieve the work we need to do because we're waiting, and that's non-productive time. So this type of modelling is termed performance modelling. I can't really tell you why it chose that name performance, but this is what it's known as, of really what we're looking at is the performance of systems as constrained by their resources. So we look at this dynamic behaviour and try and look for reasonable use of resources. But what's reasonable will depend very much on the type of system and people's different perspectives. So, for example, we might think that it's fair if everyone gets an equal share of the resource. Okay? Or equitable if people get what they pay for. So if they pay more, they get faster access to the resource or more of the resource. Affordable, how much do you have to charge? Sustainable. These days, sustainability might be particularly focused on how much electricity you're using, but it also may be the wear and tear on the system. So you have to think about these things. So understanding resources is not quite as straightforward as you might think. And there's a real challenge between what the users will typically want and what the system operators might want. Okay, so as users, what do you want from a resource? If you're trying to use a system, it's got a resource in it, what would be desirable? You want it to be timely. Anything else? You want it good quality, available, so you can get on with your work. Yeah. So from a user's point of view, we often talk about response time. So that issue of timeliness. We want to ask for the resource and then gain access to it and use it in as quick as we can. And we consider the time from when I ask for the resource to the time when I've completed my work to be response time. So that will include the time when I'm actually using the resource, but it will also include any time I spend waiting. So if possible, we want response time just to be the service time. We want it to make as much work possible as we can. So we talk about throughput, where throughput is the number of times we use that resource per unit time. And we want that to be as high as possible so that we are achieving our work. Okay? And we want to avoid any wasted effort. So wasted effort can happen because we try and use a resource and then, in fact, we just fail for some reason. So we are not able to actually go on and use it, and we have to leave the system without being satisfied. And we talk about that as what's called blocking probability. And that will represent some kind of wasted effort or disappointment in systems. From the system operator's point of view, if you think about you are running the post office, what is it that you want from your resources? So you want to make sure that they're being used a reasonable amount of time. You don't want to employ 1,000 people to work across, let's say, one town in post offices when you only need to employ 500. Because otherwise you're going to have a lot of people not working, being idle. Idle is a technical term, not a reflection on the people. And so you don't want utilization to be low, because that usually means you've invested in resources that are not being used. Equally, you don't want the idle time to be low. Utilization and idle time are complementary. So idle time be 1 minus utilization as a percentage. And equally, you don't want the system to be too heavily loaded. If we think again about the railway tracks, if they're heavily loaded, they're much more likely to be damaged. Okay, so we're usually not seeking for 100% utilization because that makes very fragile systems. So we're looking for some kind of balance that keeps the utilization cost effective, but doesn't mean that we have a fragile system. And these two requirements from the system operators and the users of the system are often in tension. And so what we do as performance modelers is try and build models that let you do what-if scenarios and try and find a sweet spot where there is enough access to keep the users happy while not making a fragile system. So how did all this start? Well, in the early 20th century, there was a Danish mathematician and engineer called Agne Erlang. And he was employed by the telecommunication company in Denmark. Now, we're talking back in the days when telephones were those tall pedestal ones where you took the little handset off and spoke in and said, please, can you connect me to Whitehall 26 or something? And you actually spoke to a person, and they took a wire that related to your line and plugged it into a switchboard connected to the line for Whitehall 26. And what Erlang was asked to do was to consider how many of those wires did you need to ensure that whenever somebody wanted to make a call, they could actually be connected. Okay. So this is a picture. This is a slightly later exchange. This is from the 1950s, but this is essentially the idea. This is the only picture I could find. And what Erlang did was he came up with this formula, which is a relatively simple formula that lets you work out the probability that you're going to drop calls, that somebody will want to make a call and it won't be possible because you haven't got one of those slots in the exchange to plug them into. Okay? And so I'm going to talk you through this formula, okay, because it perhaps doesn't look immediately obvious. So we have this parameter E. Okay, so what E is a measure of is the work that we're expecting the system to do. So when we think about the telephone calls, as the simplest example, we have two things. We have how often people want to make a call, and also how long their calls last. Okay, so E is actually the product of those two things. So it's the product of the arrival rate, how often people are making calls, and the duration of the average call. Okay, so that's our parameter E. It's named after Erlang, and it's a measure of workload that's dimensionless. And then M is our number of servers or connections, the resource that we have. So in this case, M would be those holes in the exchange board where you can plug in a wire. Okay? And so once we have those parameters, we know what size our exchange is, and we know the incoming rate of calls and how long on average people last when they're talking, then we can use this formula. So you take E, raise it to the M, divide it by the factorial, and then divide that all over this sum. And it will tell you the probability that someone who wants to make a call is not able to because there isn't room in the exchange. Okay? So it's not a difficult formula. It's very easy to apply. And in fact, it's still used to this day in call centers to understand how many people, if you know how often, for example, you perhaps want to ring up and talk to your bank or whatever, and how long those calls make, you can see how many call handlers you need. Now, in fact, we all know we don't get blocked, we get put in a queue for those systems. But quite often, perhaps the bank's not a good example. I certainly know my doctors, they have a very limited number of spaces where you can wait, and then they can work out the probability that you're blocked. So this formula is still very much in use today. It's straightforward to use once you can work out what your work is, so what that Erlang measure is, arrival rate times the duration of your request, and then how much concurrency you have in the system. So this was the start of what we call queuing theory, because Erlang based his abstraction in order to derive that formula on what's called a queue in a very technical sense. So we're used to that very informal idea of queues, of people waiting in the post office, but this is now a mathematical model. And this is the abstraction. So we assume there are some requests that arrive to the system, and they then, once the request arrives, it generates the job, the work to be done. Okay? So you can think of this as somebody arrives at the post office, and then they become a customer waiting at to join the counter. And when the job has been processed, so it waits until it gets access to the resource, it then leaves the system again, and that counts as the request being completed. Okay? And the job then is disappeared. So the job is just the customer while they're in the post office, as it were. Okay? So once we take this view of systems, we can start to observe them and derive some very simple ideas of how they're behaving. So the first thing is we just choose how long we observe the system. So this is a length of time which we'll call T. So for example, we might stand outside the post office and watch it for an hour. During that time, we will see a number of arrivals, a number of customers, a number of jobs arrive at the system, and we call this A, the total count of arrivals. We'll also see the people who leave, and that will be C, our completions. We can measure how often the system was busy. So how often was there nobody in the post office? In that time, it's not busy. When there is somebody in, it's busy. So it's serving a customer. And the busy time cannot be bigger than the total time we watch. So if we watch for an hour, the busy time must be at most an hour, and usually would be less than that. And then we can also look at the average number within the system. So this will be looking at how many are in the system for what duration, and then working out the weighted average to see how many people on average were actually in the system. We can do this for any system, just looking at it and observing it. And then once we do that, we can start to say we know a little bit more about the system. We now know the arrival rate. Remember, that was key to our Erlang loss formula, was knowing how often people wanted to make the phone calls. We know the throughput. The throughput is counting how much work you've completed, so it's the number of completions divided by that time period. The utilization is just the proportion of busy time out of the time period. And the mean service time, so the mean amount of time each job takes in service, so that would be the amount of time you actually spend talking to the person behind the counter in the post office, is the busy time divided by the number of completions. And so that gives us a very basic idea of the performance of our system. And in general, those are what we call the parameters of our mathematical model. So that's the information that we can feed into our model to then understand it a little bit more. And we do that by those observations. Now, we switch from that rather amorphous description to something that's slightly more formal. This might not look like mathematics to you, but this is kind of encoding some mathematics. So it's really the same as the picture above, but just, as I say, with a little bit more weighted meaning within it. So we have the arrivals as before, and we have the departures. And then we represent our system that's doing one job as what's called a service center made up of the server and the buffer, the place where people are waiting. So if we think back to the post office, the server is the person behind the counter, and then the buffer is the people standing in the queue waiting. This abstraction is incredibly useful because we can now start to imagine variations on it. Okay, so when we think of the post office, quite often you might have two counters open with a shared queue. Okay? So that represents having two servers in this abstraction, and we encode that in the maths. We can think of different serving disciplines. So a service discipline tells us when the server has finished one job and wants to do another one, how does it pick what next to do? Now, we're used to, and British defend quite strongly the right to do first come, first serve. Okay, so it should always take the person who's been waiting longest, the person at the head of the queue. But you can do many other things with queues. There are queues where you want to take priority order. So you might take some classes of customers before others. We would expect that, for example, at the A&E department, that they wouldn't necessarily just serve who's been there longest, but treat who's most urgent. There are some types of system where you share out the service. So everyone who's waiting may get a small fraction of time. So you might get a minute each until you've each had the service that you require. So this abstraction then allows us to build incredibly rich mathematical models. So the next thing that came along really after Erlang's formula, using this same kind of abstraction of the queues, is a formula called Little's law. And Little's law relates the number we have in our system, the arrival rate, which remember we can observe, and then the average customer waiting time. Okay, so that's the time that they're in the system, not just being served, but also waiting. So it's the time that they spend within the system. And this very simple formula is quite intuitive if you think of a completely deterministic system. So if we think of a system where perhaps somebody arrives every 2 minutes, that would be our arrival rate is 0.5. And on average, people are waiting 8 minutes in the system. That tells you, on average, you've got 4 people actually waiting. And people use this formula to determine the capacity that you need for your waiting room. Okay. It's named after Little. It was in use for long before that. The first recording that people can find is from Morris, I think in 1954, and he posed this. And it's very straightforward if you're thinking about deterministic systems, as I just did. But Morris said, I believe this will work for any system. Doesn't matter what service discipline you use. So you can use that round-robin sharing. You can take the last one. You can take the first one. It doesn't matter whether you're using deterministic times or probabilistic times using a distribution. Doesn't matter at all. And he challenged whether anyone could find a counterexample. That was in 1954. And then John Little, who was what's called an operations researcher from Boston, in 1961 proved that, in fact, it works for any system. So any type of queue like that, you can always have this relationship between the average number, the arrival time, and the wait time. So why do we sometimes use probabilities? Well, because we don't really want to track individuals. We don't know quite how any one individual is going to behave. There are different things that they can do. So, for example, you might go into the post office and change your mind and leave. You might be a forgetful person, have your service, and then decide, oh, I'm meant to buy stamps, and join the queue again. Okay? Those are all kind of individual things, but we want to be able to map, to model a whole population of people who will have those idiosyncrasies. And because we're looking at a large population, we can say, oh, 1 in 100 people go round and go round to the counter a second time. So they don't leave the system, they rejoin the queue. And so we're using probabilities to capture those random choices that people make. The other thing we don't really know when we're modeling these systems is I might go and I want to buy just one stamp, but somebody else might go and want to renew their passport. Okay, so the time requirements are going to be very different. But again, we can look at the population, and if we use what's called a probability distribution, it can say a certain proportion of people will be very quick, a certain proportion of people will take a really long time, and then other people will be somewhere in between. And I think we're all fairly familiar with the normal distribution. You can think of the bell curve. We don't tend to use this for performance modeling. We tend to assume most people are towards the short end, but then you've got what's called a heavy tail of people who take longer. So that's the exponential distribution. So let's imagine our post office again and see what difference the randomness makes. So if we've got our post office, and suppose that one customer arrives every 2 minutes. Okay? So each of these marks on the diagram, these are just illustrative diagrams, not perfect to scale or anything, but here we can see that they're coming at regular intervals. And let's imagine that they take 1 minute each for service. Okay? So we can see we get those blocks there, which is when the person behind the counter is busy serving a customer. But because they only come 1 every 2 minutes, And because we exactly take 1 minute, then there's going to be gaps in between. So what's the utilization here? It's 50%. Idle time 50%, utilization 50%. What about the average queue length? 0. So nobody is queuing. Now, sometimes we would count the person in service in queue, but you interpreted it the right way for me. So yes, it's 0 here. So that's just right. But now if we make it more random, so here we've got, and I say this is just illustrative, but let's imagine we have the same arrival rate over an hour, but we take a small segment. We've got the same number of arrivals here, but now they're bursty and they're not so regular at all. And then we add in service, and some of those services are less than a minute and some are longer, but then now we're starting to get queues building up, because you can see the red is when somebody arrives and the person ahead of them is still in service. And so the red period is when they're waiting before they gain service, and then they have their own service period. Okay. So what's going to be the utilization of this system? It's still 50%. But what's going to be our queue length? Don't look at the diagram exactly, because this is just one sample. But
about 5%.
You think the queue length will be, well, queue length can't be a percentage.
Oh, well.
It is 0.5, well done. So there is a formula that lets us work this out. The formula is based on that measure of work that Erlang decided, the E, that looks at the arrival rate multiplied by the average duration, and that we know that then utilization is 1 minus E. So that stays the same whether it's deterministic or random. But our average queue length will change as the proportion of the arrival rate and the service rate gets closer to 1. So if we were to increase the amount of time with the deterministic system, as long as we stayed less than 1, we would never have a queue. But with the random system, using the exponential distribution, if the amount of time that people took on average approached 1, we have a queue that tends to infinity. Okay, so the randomness, that variability, makes a big difference to our experience of these systems. So looking at the queue again, and the very basic one, what we do is we model it into a representation that's called a Markov chain. Okay, so this is the states of the system. And for a queue, what's the state of the system is how many people are waiting. Okay, so we start with 0, we have an arrival, we move on to 1. And then we might have a departure, which we traditionally call mu, and we go back to 0, or we might have another arrival. We saw this with our post office starting to stack up. And so we have these, and then this can be translated, this graph that we have translates into a matrix. We do some linear algebra, and we get the answers that we just had. So we can know the average number of people in the queue, the response time, all these measures, very straightforwardly from this abstract notion of the system as a queue. And what's even better is most of our systems are not a single resource. Okay? We would have multiple resources. If you think about going through the airport security, we go through a number of different queues there. And so we can stack these up as we look at our system. We represent each resource as a separate queue in the queuing theory sense, and we map how they interconnect with each other. So if the customer who leaves the top left-hand side queue, he has some probability of flowing straight on to the one on the right-hand side, or he may go down and exit a different way or join the one on the below on the right-hand side. So we have these different, what are called routing probabilities. So we can build really quite complex representations, but we still can represent each one as a queue. And that very simple mathematics, remember the birth-death process and ways of deriving formulae about what's happening in that queue just from knowing those parameters, arrivals and departures. And we can do that even with networks of queues. So this is the great beauty of queuing theory. Queuing theory is a really elegant piece of mathematics that allows us to build the description compositionally and then actually solve it compositionally too. So we don't need to really study it as a whole. We just have to understand each queue, how it's behaving, and how they interact with each other. Now, how they interact with each other is very limited. All that can happen is one customer flows from one queue to another. Okay, so it's quite a restrictive form, but because of that restrictive form, we get really elegant mathematics that scales beautifully. And this was highly effective for most of the 20th century. And as such, it had many uses. So in the early 20th century, the biggest use for queuing theory was actually what were called job shops or assembly lines. And people wanted to study how to make them as productive as possible. So they wanted to look at throughput. And looking at how different components or widgets were being constructed by the different stages of the assembly line, they could tune it to be as efficient as possible. Perhaps adding an extra machine or something if they realized there was a bottleneck. And then what happened in around 1960 was people realized this was a very good way of modeling what happens inside computers. So when you make a request to a computer, it generates activity for both the processor and the disk and possibly the I/O mechanism sending communications to other computers. And up until about the 1980s, this queuing representation was very useful for that. And that knowing how big your buffers need to be, for example, is really important for making sure you don't lose data as you process it, that you've always provisioned enough space for the data that you need to store while it's waiting to be processed. And so queuing theory was used a lot for performance modeling of computer systems. But then in the 80s, what happened was that we started to have the internet much more. And so our systems became much more interconnected. And so, for example, you might think nowadays you're using a web application. Let's say you want to book a holiday. So you would perhaps put some details into something like Expedia, and it will then shoot off a number of queries to different airlines who have an interface that lets query their database to see, do they offer a flight? What price will it be? What's the time scheduling? And that will be happening to multiple airlines at the same time. And they will respond to the web service that you're using and then be displayed. If the system is very slow, then jobs may get dropped. So, for example, if Expedia is trying to query and then it finds Lufthansa just doesn't respond, it will give up on that job, okay, and just show you what it's got. And so we have a very different kind of world that unfortunately does not fit with the assumptions that were there within our queuing networks. So queuing networks have that very sequential way of working. You used one resource, you flowed through that connection into the next resource and used it. So in particular, classic queuing theory only lets you use one resource at a time. Jobs cannot be merged and split. You can't have one job that then generates queries to multiple databases at once. You can't have queries come back and be joined together. Patterns of arrival and service has to assume that each arrival is independent from the previous one. And in particular, customers cannot change their behavior by what they see. So this also explains why classic queuing theory is not very good for humans, because we change our behavior. If we see a big queue, we decide we're not going to join it, or we join the queue and then we give up. Or we'd get to the front of the post office and we decide, I'll leave that complex task to another day because there's 10 people behind me. We alter our behavior, and queuing theory assumes that that doesn't happen. So what was needed was new ways of building our models. Okay? So Just as previously we had those cues, that was very nice, it was straightforward, and then it gave us a pattern for how to build mathematical models, we now needed new ones. Okay. So these are new abstractions. So like we had the cue abstraction, now we need something different. And the key difference now was that we had multiple things happening at once. So we have what's called concurrency. As you might imagine, computer scientists were quite interested in this because it affects many aspects of computers, how they're working, once you've got this ability to interconnect and bring things together. So as well as, from my point of view, looking at the resources, we also had to start looking about the correctness of systems. And so there was quite an explosion of new ways of describing, particularly computer systems, to take account of this concurrency, this parallelism that was suddenly available. So some are called Petri nets, there's things called event structures, but I'm going to talk about something called process algebras. So process algebras are an algebra in the sense that you have certain operators, just as you do with plus and addition and multiplication in regular algebra with numbers. But now what we're combining are small processes, but they have to follow certain rules. And then if we stick to those rules, we can reason about how the composite will behave, just as we do with algebra with numbers. And what's more, we can develop these process algebras, these ways of describing, so that we maintain a close relationship with the Markov chain. So remember, our Q turned into a birth-death process. So we had that abstraction, and then we could build a Markov chain that gave us the answers we needed. So we still want to be able to do that. And so we do that, but the structures of the Markov chains will be slightly different. So the first language to do this was something called performance evaluation, process algebra. So we're still focusing on that performance idea of our resources. And you can think of this as a programming language. It's a very simple programming language. How many people program? Okay, yeah. So it's like a programming language, much simpler than most of the ones you use, I'm sure. But it doesn't compile into machine code. It actually compiles into mathematics. So just like you do with a programming language, you describe the program you want, the model you want, in this case, the process you want, and then you give it to another piece of software, a compiler, and this time what the compiler will give you is a mathematical model, a Markov chain. So what the process algebra is focused on is the components within our system. So components within our system may be customers, they may be resources, and actually now more flexibly than we had with queuing networks, we can have processes that are sometimes resources for other resources, other customers, and sometimes customers themselves making requests to other resources. So we start to have a lot more flexibility in the type of things we have and how they interact. Okay? And as I've mentioned, we compile down to Markov chains. So here's a queue described in one of this language, a very simple example. So it's just writing down in words very much what we had with the queue before. So we have an arrival. It arrives at some rate. We've called the action accept. So arrival is accepted into our system. We start off with a system where there's 0. When we have an arrival, we move to a system where there's 1. And then for any value I, we can either have an arrival or we can be served and depart. And then we have a server who is actually governing the speed at which the service can happen. Okay, so this is just to show you that we can capture the things that we did before. This translates into a Markov chain like this one. So it's exactly the same process as we had previously. But we can now start to have much more complex components as well. So here, again, it's a very simple example to make it fit on one slide, but this is some application making use of a web server. So the application may have different activities. So we often in performance modeling, when a user or an application is doing something independently, we just call it think time. So with this application, the person using it is thinking, and then they may do some local interaction that just works on their local computer in their browser. Perhaps they want to update some of their personal information. Or at the end of that think time, they want to actually request something from a remote service, the web server. And we can see that goes through the request, service, and respond there. Conversely, the web server sits and waits for requests, will carry out the service, and then send a response back. This is very simple. I've just drawn it with one application user, one web service, but typically we would be thinking about hundreds of application users, so multiple copies of these resources, and perhaps tens of copies of the web service available. And then we can study if you can see that at the end of the think, we're using one of those probabilistic choices. So some proportion of work will be local, some proportion will use the web service. As we alter those proportions, we can see how responsive the system is. So just as the queuing networks were, we're building the model from smaller components. Okay, so we use submodels and then we build up a larger model of the whole thing. But now our ways that they interact is no longer that flowing from one queue to the next. We can see that we can make them interact. And in fact, I only had 2 components, but if I had 3 components, I might make them synchronize. So you might use 2 resources at the same time, or you may force that 2 different users have to synchronize in order to use the resource. So we have a lot more sophistication in terms of the behaviors that we might generate. Unfortunately, and there has to be a price to pay for this greater expressiveness, we can't decompose. Remember, the queuing networks were lovely. We just modeled the individual queues, and then we said, oh, well, this is how they interact, so this is the overall answer. That doesn't work. We now have to model it as one big mathematical system. But, as I said before, we use software tools that build that mathematics for us, and then there are well-established tools for actually solving the Markov chains in these general forms. Sometimes it takes a long time, but we can get the answers. And what's more, we can then build tools. This is the tool that we have for the Pepper language. So you can see on the top left-hand side, there is the editor window where you describe your model. And then what we're seeing on the top right-hand side are some results telling you the throughput for this system. And as we altered the number of web services and applications, we would see different throughputs, different values. And this is all done just by you describe the model. You have to do that work of doing it, and then you press a button, and all the generation of the mathematics and the calculation of the metrics is done for you automatically. So this was great. It extended our view way beyond what had been done before with queuing networks. And so we started to get some really interesting examples. So one of the first, and one that surprised me, was some people wrote to me from Belgium and said, thank you very much. You really helped us improve how we move freight around the canals in Belgium. Because when you think of moving things around boating systems, locks and bridges are those kind of resources where you're going to get bottlenecks. And so they use Pepper to build models of that and then tune the system so it worked a little bit more smoothly. Just as with the job shops, we can look at the modern examples of things like robotic work cells and work out how they can satisfy what features we need. In this particular case, we were looking at how quickly the arm needed to move. There were certain constraints within its physical building of how it could move, but you needed it to pick things off a conveyor belt to keep the work cell working at optimum value. Cellular telephone networks don't quite work the same way as those old exchange networks, but you can still have problems that there's not enough frequencies for all the calls that you need to make. But it's more complex than it was with Erlang. And so colleagues in France this was back in 3G, it's a little better now with 4G and 5G, but the 3G really had to worry about how many frequencies you had and how many people you could serve by your cellular towers. And so they looked at that and the positioning of the towers to meet demand. And then some colleagues in Italy were looking at an onboard computer system for, in fact, buses, which had lots of sensors. You know, vehicles now are really big computers, or actually many computers. This had multiple sensors, but they wanted to know that the performance was sufficient, that alerts would reach the driver as quickly as needed to safely be able to take action when something had gone wrong. And often our work in performance modeling is about that response time. Are things happening quickly enough? Much of computer science, we worry about, are the right things happening? So we worry about correctness. But in our case, we're worrying about, is it quick enough? And that's why my chair title is quantitative modeling, because much of computer science is just qualitative modeling of looking, is the right thing happening? But we worry, is it happening fast enough, or is it using too much resource? So we actually add in the quantities. And then even more surprisingly, these techniques started being used in completely different domains. So, for example, biological systems from the cellular level, and the picture on the left-hand side is thinking about cell cycle, and the picture on the right-hand side is Japanese knotweed. So that's what we call an invasive species. So it might seem strange to think about these. We don't really think of those as resource-based systems, but these systems nevertheless have resources. So within the cells, the resources are the proteins, the actual kind of raw materials that you need to do the processing within the cell. Within the ecological system, the resource may be space, physical space, for things like a plant to grow, or quite often it'll be food supplies or nutrients within the ecology. So the same modeling techniques start to be used for these different systems. And because we have these languages, we can tailor the way the language is formed to be more natural for the people, for example, working in biology. So we would use primitives that make sense to them, instead of using things that originally we were looking very much at computer systems. So if we take a small example from the cell biology, this was the cell cycle. We have a model that's based on one that was published purely as a description by Goldbetter in 1991, and it's looking at how a protein called cyclin governs our cell cycle of when cells divide to form new cells. So we have the protein C, which is cyclin, and you can see that up at the top. I have to get my left and right. So that's coming in at from the left-hand side. Below that, the level below, you can see what's called a kinase, which is affected by the cyclin. And then below that, you see a protease. So a protease is like an enzyme that, in this case, promotes the degradation of the cyclin. Okay, so that's the bottom. And this is a negative feedback loop. So your cell generates cyclin. You have the kinase in active and an inactive form, but when we have some cyclin, it promotes the active form. We have the protease in active and inactive form. When we have the kinase, it makes more active protease, and then the protease actually speeds up the degradation. So it's switching the whole thing off. So that's this. And you can see we have these different reactions, R1 to R7, within the system. And then this is what's called the BioPepper model. Now, I don't expect you to read this, but just taking the first line, you can see the first reaction, alpha, increases the amount of cyclin we have. That's what the up arrows say. Whereas the action alpha 2 decreases the amount of cyclin. And so we can describe our system. We have the next two are the kinase, and then the X equations are for the protease. Okay? And then at the bottom, we describe how those all interact. And a shift when we move to the biology is we're not using Markov chains now. We actually compile to a different form of mathematics. So we actually compile into ordinary differential equations. Because what we do with Markov chains is we count things. But when we're looking at cells, there's way too many molecules of protein to want to count them. So instead we work in terms of concentrations, and we use continuous mathematics, ordinary differential equations. But this is just generated for us. We do that description, press the button, and we will get this set of equations which we can then simulate and understand. So this is when it's well regulated. So the Ks have a certain value, and you can see the nice cycle that we see. The red is the cyclin. As it increases, that then promotes more active kinase, that switches on the protease, and as the protease, the green increases, you start to see the red drop. And then it goes through. And this is what governs our cell cycle. And if we have a different value, so something has happened, that perhaps one of those proteins is undergone a mutation, so it cannot bind so efficiently, so the rate of these actions have changed, we lose the oscillation, and we lose regular behaviour of cell cycle. So future challenges. Many. There are just many systems, and resources are key for all of them. But the one I wanted to particularly talk about was AI, because this is one that we're hearing a lot about at the moment. So in recent years, generative AI, large language models, have been in the headlines a lot. And mostly this has been because they have astonishing capabilities. But more recently, a little bit because they have astounding uses of resource as well. So these are very expensive models to run, both in cost, in energy, computing equipment, in every way. So as a performance modeler, I was very interested to understand, how did this happen? Why did people not notice that these were going to be such huge consumers of all those resources? And the question is I'll give a couple of examples. So, this is using so much electricity that Google's talking about building nuclear power plants to supply the data centers of the future. Even in Nature last week, there was a paper looking at the energy consumptions that AI is likely to demand as its use is increased things. We know that a ChatGPT query takes 100 times more energy than a Google search. How many of you use ChatGPT? And do you think about how much energy it's using? If you look at the Nature paper, it actually tells you how many operations you can do on the typical battery life of your phone. And it's really interesting seeing when you're using Google versus ChatGPT, etc. Llama, which is another of these large models, produced 539 metric tons of CO2. So they're doing serious damage to our climate as well. But performance for a long time was just this use that is the normal use of performance, so not the performance modeler's idea of what performance is. It was about how well does it do what I would like it to do. And so we had a lot of these headlines about 2 years ago about ChatGPT-4, about how it could pass the Scholastic Aptitude Test and law exams, medical exams and things. So the focus was all on capability. And this actually comes out of the community that developed these systems. So if you go back even 20 years and look at natural language processing systems, they have been driven by league tables of looking at how well systems do against various tasks. And what did we learn at the beginning? What gives you the best user-defined performance? Infinite resource. Okay, so that these systems almost have that baked into them, that they're going to, because they're just competing from the user's point of view without thinking at all about their resource use, to get better, you're just going to keep adding more resource. So we can see this in all aspects of these models. So this, I don't have slides these slides with DeepSeek on yet, but this was up to ChatGPT-4 last year. And this is looking at the internal structure of these models and how many connections they have. And you can see that they're growing. They overtook the size of an ant brain back in 2018, surpassed the rat brain soon after that, and is heading up towards the level of a human brain. If we think about the data, another resource that we perhaps should think about more than we do, and I must say traditionally in performance modeling, we tend to think of data as just workload. We don't actually think of it as a resource, but we need to with these systems. Here we're looking at all data. Human text is that green line at the top, and these systems are consuming all that resource. And then here is cost. So on this graph, we're looking over time along the x-axis and price in US dollars on the y-axis, and you can see that it's growing. This is a logarithmic scale. And this is the cost. It includes buying the computer equipment, but also paying for the electricity to run it, the cost of servicing it, the rest. So performance, when you look at their literature, their scientific literature about these models, performance is mentioned a lot, but as I said, always against these benchmarks of behaviour. So there's no consideration for resource. So how do they judge them? They judge them by accuracy or precision, or sometimes there are standard question answering texts and things, and they keep these league tables. And this has led to these ever larger models because you can put as much resource in as you like, and you're considered better if you've done better without considering the cost. Yeah. And this is leading to a lot of consumption, and in recent years, concern about the resource consumption. So we're starting to see efforts to reduce it, but at the moment it's very handcrafted and rather ad hoc. So this is really a call to arms for myself and other performance modelers that we need to think about these systems. But unfortunately, it's not so obvious. So when you think about our systems, right at the beginning, we talked about making a crest and getting a response. But how do we relate that to training one of these models when they take a month to train and they use many hundreds of computers to do that? Where do we define the performance metric for that? Things like response time makes no sense. We sometimes say latency, the delay in getting an answer, doesn't make sense. Even utilization gives us little insight because the processes that are being used during the training are often close to 100% utilized. So we have a really big challenge here. No answers yet, but people are starting to collect data. So these are graphs that were developed by the site LLM Stats, and these I collected on the 6th of March, so just last week. And this is a site kept by Berkeley, and all they're doing at the moment is cataloguing these systems to understand their use of resource better. So on this graph, on this one, the how good you are, the performance from the user's point of view is the y-axis, and the performance, the parameter for the x-axis is how big your model is, how many parameters it has. So you can see that DeepSeek is actually there outperforming the others, but also much bigger than the others. Okay, so that tells us something about more connections you put in, DeepSeek is doing better. I don't know how many of you know about DeepSeek, but it has much better performance on reasoning tasks and things like that. And then this one, it changes around that the x-axis is the behavior against the benchmark, and this is a question answering benchmark, and the y-axis is the cost. And we see that ChatGPT is way out there with the cost. It is by far the most expensive. And we see the later OpenAI models, O1, etc., are lower cost but much better performance. So we're seeing improvement in these systems. So DeepSeek hit the news this year. So it hit the news because its performance from the user point of view was much better. But what interests us as computer scientists was its performance, in my sense, was better as well. So it uses far less resources. And why was that? Well, it's that old saying of necessity is the mother of invention, that they didn't have access to the same scale of computing resource as the American tech giants did. And so they had to look at better ways of using the resource they had. We're still fully understanding what they did, but one of the things that they do is they make better use of that idea of concurrency, of doing multiple things at once. They really handcraft things to really ensure that there is efficiency when they are using resources. And so careful engineering has led to both excellent performance from the user's point of view, but also better performance from the computer scientist's point of view of using resources. So to conclude, resources, access to them, and contention for them actually play a major role in many of the systems that we interact with. Not one that we're always aware of, but nevertheless there. And mathematical models, such as the ones I've talked about, can really help us understand those resources. Failure to consider resources can lead to unrealistic expectations from users, this idea that we have infinite resource, we can always just get what we want, and unlimited costs for systems providers. And this is what we have seen so far with most of the large language models. But even simple mathematical models, such as Erlang's last formula, can give us insight and help us use resource more effectively. So finally, thank you very much. I really appreciate your attention. I also want to thank all my collaborators and students. There were too many to list here who've worked with me over the years developing Pepper and the many other models that we've used. So thank you.